I'm going to give an example of running an ANOVA. So we're interested in whether there's a difference in math skill scores based on marital status. And you can see that we have 3 categories of marital status: married, single, and divorced. And when we want to compare means, the mean of math skill scores, by more than 2 groups, we know we need to use an ANOVA. So let's go ahead and get started on the 9 steps for an ANOVA. So step 1 is to look at our data, right? So we know that the independent variable here is marital status, and the dependent variable is math score. Now, this is another one of those cases where we can't enter the data as it appears, as it is given to us, because the dependent variable is right here, all of the math score. So we have to slightly adjust the way we enter the data as we did for our t-test, and you can see here that I've entered married, single, and divorced. Now, within Stata, I can code married, single, and divorced as a nominal variable and leave it as such. In this particular case, I coded married, single, and divorced by adding, I coded as interval data. And you can see over here I added value labels, if you remember how to do that. And actually, in this particular case, coding it either way works. So that is why I listed marital status as interval, because 0 is not the absence of a marital status, so this would be interval data, whereas a 0 math score would mean that you had absence of a math score, right? So then we move on to our assumptions, and as you know from the handout, we have 4 assumptions. So the first assumption is that the dependent variable is interval or ratio scale, and we look right up here and we say we check the data, yes, thumbs up. The second assumption is that the sample means for each group within the independent variable must be normally distributed. Now, to check this, as you remember, we'll have to select cases and look at a histogram for each of those 3 categories separately. And I'm not going to go through that here because my video keeps cutting out when I take too long. You all know how to do this. We've done it a number of times. But remember, you're going to need to select cases and look at each group separately. The third assumption is that the samples are independent of each other. And in this case, we know this by looking at the data and thinking about it. An individual cannot be both married, single, and divorced, right? And so we know that these represent different individuals. So we can say we checked the data and we met that assumption. And then the final assumption in an ANOVA is that there is homogeneity of variances. And homogeneity of variances means that the variances are equal. And we have to do something that we haven't done before in order to do this. And we have to run an analysis that checks the Levene test for homogeneity of variances. And so in order to do this, we actually go ahead and do our full analysis. And I want to show you how we do that now. So we click Analyze, Compare Means, like we did for an independent samples t-test. But as you see, we go all the way down to the bottom for a one-way ANOVA. Now I already ran this, but let's pretend like I hadn't. And let's bring these variables over. So we know our dependent variable is math, right? And the factor, or the grouping variable that we're interested in comparing, is marital status. Now before we go ahead and click OK, that would just give us only ANOVA results. But there are a couple of extra things we need to know. One is our post hoc analysis, and as the book points out, we will use a Tukey. So this will tell us something I'll describe in a second. And the other is we want to click on options. And here is where we get our homogeneity of variance test. So we're going to click on that, and this will let us know whether our data meets assumption 4 or not. But we'll also click on descriptives, because this will give us a sense of, well, what was the mean in each of these different categories. So now we can go ahead and click OK, and we get some results. So first we get our descriptives, and you can see we get the mean value by different categories. So married folks had a mean math score of around 35.7, single had 37.9, and divorced had 33.1. What we're really interested in for our assumptions is this test of homogeneity of variances, and we have that right here. And so what we see is we get a Levene statistic. Where is my finger? Oh, there we go. We get a Levene statistic we get our degrees of freedom, and then we get a significance value. And so we're testing homogeneity of variances. And as you remember, our research hypothesis, or our hypothesis of interest, here would be that the variances are different. They're not equal. And so therefore our null hypothesis would be that they are equal. And so when we get a p-value greater than 0.05, we fail to reject the null, and we say that we met the assumption. So our homogeneity of variances here, we check the Levene's test. I wrote in 0.531, p equals 0.597. P is greater than 0.05, so we fail to reject the null and conclude that the variances are equal. Yes. Okay, so we've met the first two steps. Our third step is to state our hypothesis. Here we would say there will be no difference in math score based on marital status. And our research or alternate hypothesis is that there will be a difference in math score based on marital status. We know that our test statistic is our one-way ANOVA, and then we would draw the decision rule. Now, calculate our test statistic. We've actually done that, if you remember. So our test statistic right here is hidden. It is our F value. So our F equals 0.347. Our degrees of freedom for that test statistic are 2 and 18. So if we go to calculate test statistic, you will see that we have F equals 0.347 and degrees of freedom 2 and 18. So our next step is the p-value. And where is the p-value? Well, if you remember, it's right next to our F value. So our p-value is 0.712. So I will write that in step 7. And then step 8 is the statistical decision. And we know that a p greater than 0.05 means that we fail to reject the null. So what can we conclude from this? Well, we can say that we computed a one-way ANOVA comparing the math scores from individuals from 3 different levels of marital status: married, single, and divorced. No significant difference was found. F with degrees of freedom 2 and 18 equals 0.317. P is greater than 0.05. And we say that the math scores did not differ significantly based on marital status. Now you can see I started to interpret Tukey's, and I forgot to show you back here where that Tukey's came from and what the heck Tukey's means. So our F statistic in our ANOVA is telling us whether the difference between groups is greater than the difference within groups. But this is looking at all groups together. So this is telling us, are these 3 groups as a whole different? If we had 5 groups, it's telling us, are these 5 groups as a whole different? And that's an interesting question, but we might also be interested to know, okay, so maybe there's no difference between all 3 groups as a whole, but what if the difference between married and single was actually significant? It's just that the difference between married and divorced wasn't, and therefore the difference between all wasn't different. So we want to look at our Tukey's, and our Tukey's is allowing us to do a number of pairwise comparisons, and by pairwise we mean 2, right? So we can compare married to single and married to divorced. This is telling us the mean difference between those 2 scores, and then it's telling us the significance level. And if we look down all of these significance levels, we can see that none of the pairwise comparisons in this case are significant. So not only is there no difference between all 3 groups, but there is not a difference between any of the pairwise comparisons either. So the way that we would talk about that is we would say Tukey's, HSD, and HSD is honestly significantly different. Tukey's HSD was used to determine the nature of difference in math score by marital status. This analysis revealed that both the overall difference between the 3 math score means as well as all of the pairwise comparisons were not significantly different. Now, if we wanted to start getting even fancier and add a little more to our interpretation, we could come up to our descriptives, and we often do this when there is a significant difference, is we might want to say those who were married had a mean math score value of 35.7, those who were single, mean math score 37.9, and those who were divorced, 33.1. This is why we include our descriptive statistics here. And often when we find a significant F value, we're really interested in doing our two keys to see, okay, so maybe there's a difference between all of them, but is that only because there's some pairwise comparisons in here? So again, we always want to run both the overall ANOVA as well as our two keys comparisons. And this test of homogeneity of variances, we need to click on that box, and this is how we get assumption number 4 in step 2. So I hope that is helpful for you as you go through your research notebook and attempt to look at and run an ANOVA, looking at whether vitamin use differs by age, or whether age is different based on category of vitamin use, is the way that we phrased it. Thank you.